Absolutely. Yeah. Excellent. All right. So, all right. I'm not sure if what I have to say is relevant to philosophy, but maybe we can see. So, this is how it all started. I was teaching a course on. Actually, this is not how it started. Somebody invited me to the Rotary Club at Hong Kong to give a talk, and he said there are going to be a lot of lawyers there because they belong to the Rotary Club. So can you give a talk about statistics in the courtroom? So I thought about, I was teaching a course on information theory, and it just occurred to me that perhaps the courtroom scenario would be a good example for explaining these particular ideas. And then as things progressed, I had to go into the hacking situation, and it turns out that the hackers are also very cognizant of information theory. Not as cognizant as they should be, but they do something that is, so that's the talk. So let me give a preamble. So the adversarial scenario, can you see it? Yeah, can you see this? Yeah. The adversarial scenario of a courtroom wherein a prosecutor interrogates a witness offers a platform for introducing the notions of entropy, information, and something new I learned, Extropy. It appeared in Statistical Science of all the journals, and I thought it was quite interesting. That is used in communication, coding, and scoring theory. Extropy is used in scoring theory. And a topic of interest, hopefully, in big data and computer security. So that is a hope. So the purpose of this is an expository talk, is to articulate as to what exactly these notions mean, how they emerged, what is their merit, and what are their deficiencies. In other words, this is a talk about the musings of an unconscious information theorist. A lot of books on information theory start with Shannons Formula, and then they just go on about it. Particularly, you remember Tom Cover at Stanford. He's written, he's no more alive. I don't know if you know that. He passed away. But his book is full of formulas and everything. So, I don't mean he was unconscious, but it's more about me.
Did you use his book?
I never used his book. I never did it. I just went to ground floor. I went all the way back to the basics to see what was happening. So here's the coding and keep interrupting, transmitting scenario. So I was giving a talk in Budapest, Hungary, at the Applied Probability group which meets. So I had to make it a bit Hungarian. And also the gentleman who invited me to the Rotary Club, his name is István. He's a Hungarian. And so the idea is this. He wants to secretly communicate a message, say X, which says, let's meet for a drink, to his friend Flora. Flora is a Hungarian name. So I thus codes X in strings of zeros and ones, like drink could be 1001, meet could be 0011, and transmits these to F via a sequence of dots and dashes. That is what a Morse code is. Because of atmospherics and other factors like hacking, by jealous friends and other admirers of F, the coded message gets contaminated and is received by F as a perturbed string of zeros and ones. So the original zeros and ones get all jumbled up, and so what F receives is a jumbled version of the coded message. So F has a decoder which invokes on the transmitted but contaminated message, and thus receives Y instead of X as István's message. So she gets the wrong message, or she gets a message. What sense should she make of Y? And what did the I really intend to communicate? So here's the schematic. So here's the message X. It's coded. then it goes to a transmitter, there is the disturbance and hacking, and there is the decoder, and it's received as Y. So information theory arose in connection with such problems of coding, communicating, and decoding. The theory enabled a comparison of the efficiencies of coding by measuring the rates at which the coded messages can be conveyed using different schemes. The smaller the code length, the faster the rate of communications. Also, short and smart codes are less prone to contamination and hacking. So basically the subject started from that kind of a problem. And of course, since I was in an applied probability group, a lot of people do queuing. So I said telephony thus spawned two areas of applied probability, queuing theory and information theory, and that is true. Queuing theory had its origins in telephone problems. Certainly information theory had it.
So the number, is it the length, the number of zeros and ones, is that the code length? Would that count as the code length?
Yes. The shorter the, so I'll give you another illustration.
Okay, I'm just curious.
Right.
Why, is it possible to explain why shorter codes would be less prone to contamination?
Because there are fewer digits to contaminate.
But if I contaminate one, then...
Oh yeah, the message is equally lost. So what they wanted to do is to have the shortest code lengths for communication. So the word A, which we use constantly, should have a very short code length. But whereas something unusual, I have an example later on. But that's the idea. But let me also just say that, okay, keep asking. So here it is, to answer your questions. Alphabets like A or words like Trump occur commonly, whereas others like Zoroastrianism, where I was born, occur rarely. Thus, to achieve transmission efficiency, the former should be assigned a small string of zeros and ones, whereas the latter long strings. Okay, we'll get to this. The other thing, of course, is probabilistic ideas play a role here and enter the picture for efficient code development vis-a-vis the frequency of appearance of alphabets. Alphabets that appear very often have a high frequency, and so they influence this. And of course, just to recall, Markov processes were invented when they tried to understand Eugene Onegin's poetry. So there are examples of where art and literature has played a role, probability has played a role there. Okay, so probability also enters the picture because disturbances in transmission called noise. The noise also is probability. For example, what is F's probability that I said, let's meet for a drink, when F has received a coded Y? The first matter leads to the probabilistic notion of the amount of information in a message, and that's the second, the capacity of a communication channel. In some sense, this was Shannon's biggest contribution. The one above it, which is what I'm going to talk about, how much information is there in a message, is what I'm going to talk about, and try to give you a feel for what it is. The focus of my talk is on the first matter, the notion of information and how it is measured. So, a little bit of history. Credit for the rawness of the idea of information must go to Fisher, who in 1921 proposed the reciprocal of the variance of the distribution of an estimator as the amount of information provided by the data. So frequent statistics have the notion of information. And of course, then there is the Shannon's notion of information. And people say that what Fisher said was different from what Shannon said, and indeed it is different. But the idea was essentially, I think, Fisher's, who essentially came up with the reciprocal of the variance as the amount of information. So then, Fisher-Hartley, in 1928 of Bell Labs, he suggested, so I think this is the person who really had the guts of the idea. He suggested log 10 to the base 1 over px as the amount of self-information provided by the random variable x when it is revealed as x. So that credit really goes to Hartley. Now, why did he choose log 10 and why did he choose 1 over px?
So these are two completely different ideas.
Two completely different.
These two ideas of information.
But Hartley may have been influenced by Fisher. May have been. But there's something more coming which most people don't know. You talked about Turing, right? Mm-hmm. And we know George Barnard. Did you know they came to the US to learn? Turing came to the US, to Harvard, and George Barnard came to Harvard to study. The war happened, and so they went back. And I'll get to that, okay? So there's a little bit of history. So why did Hartley choose log 10? Well, he was working on telephones. The first point to note is that Fisher used 1 over variance of x, and Hartley used 1 over px. So there is some connective here. The second thing, Hartley used the base 10 because the telephone had 0 to 9 digits, taking equiprobable values, making log 10 to the base 10 equals to 1 as the unit of information, which in those days was called a Hart, after Hartley. Shannon came and changed all this, but not too much. So I say Fisher and Hartley set the stage. And so what did Shannon do? Shannon retained Hartley's log 1 over px, but changed his equiprobable 10 digits to an equiprobable 2 digits, and the base of the logarithm changed from 10 to 2, giving log 2 to the base 2 equals 1 as the unit of self-information provided by a Bernoulli X. It was called by John Tukey a bit, and I think John Tukey and Shannon were close colleagues. So there is a little bit of connection there. So what happened? Well, Shannon spearheaded a theory of information based on the above. Khinchin, the Russian, followed by Kolmogorov, articulated on the mathematical and philosophical underpinnings. So Kolmogorov had much to say, not well known, but Khinchin, of course, is well known because he essentially axiomatized Shannon's ideas. But Kolmogorov started giving some meaning to all this, and I'll get to it as we move along. So the first question is, why did Shannon and Hartley use log 1 over p of x as the metric of information? That has raised a lot of concerns. Khinchin was comfortable with taking refuge in the mathematics. Kolmogorov became cautious, but also generous in a way that he kind of praised Shannon. George Barnard, the statistician who some of us met, I'm sure, Glenn, you met him? George Barnard, yeah. He was a little bit more English, so he kind of came strong. So George Barnard channeled Shannon's formula. And Rainey later on reacted to Barnard and suggested an escape via improper probability distribution. So Rainey's famous paper essentially justifies all this, but for him to justify this, he has to get into the idea of improper distributions and those kind of things which people may not like. So let me motivate all this. Let me just...
You want to elaborate on what you mean by Khinchin taking refuge in mathematics?
He just wrote axioms.
No.
He just took Shannon's formula, put down a few axioms and said, this is the only formula that will satisfy these axioms. Okay? So his paper is very well quoted, but no motivation.
Well,
Kolmogorov did come up with motivation. Kolmogorov did give meaning. Despite being Kolmogorov, he was also interested in down-to-earth stuff, as you probably very well know. All right, so let me give a motivation and show you why this formula comes up. And I believe there is Shannon's ideas here. So think of two suspects, one of who is certainly guilty, is hauled in a courtroom for pinning down the culprit. So there are two suspects. One of them is certainly a guilty person. There is a witness who knows the culprit. So expert witness knows the culprit, but is under gag orders to give only truthful yes or no answers to the questions raised by the prosecutor. The witness cannot reveal any, I mean, I've been an expert witness and they strictly tell you answer yes or no, don't say anything more. So the witness simply has to answer yes or no. The witness is prohibited from releasing any knowledge beyond the yes-no responses. So that's the scenario. Lawyers think that's not quite realistic, but let's just assume so. The prosecutor, of course, has no clue, or at least we assume he has no clue as to which of the two suspects is guilty, but there is one guilty one. He knows one of them is guilty, or she knows. The prosecutor suspects both are equally guilty. So the question is, what's the minimum number of questions that the prosecutor need ask the witness to pin down with certainty the guilty suspect? So there are...
Actually, you're assuming one is not guilty.
One is not guilty. Yeah, there's only one guilty. Yes, there are a lot of caveats like that. And in fact, one can change the foundation of information theory by bringing in those kind of issues. So, thank you. The answer, assuming witness is honest, is just one. The witness could also lie, but let's assume the witness is honest. The answer is simply one. Why is that? Because all the prosecutor does is says, suspect labeled one guilty, and if this person says yes, it's done. If she says no, it's the other one. So the answer is straightforward. If there was only one suspect, of course the prosecutor doesn't have to ask any questions, because the suspect is by definition the guilty one. If the number of suspects is 4, then the minimum number of questions the prosecutor needs to ask is 2. Why is that? All the prosecutor has to do is so partitioning is very important. Partitioned in 2 equal groups, each of size 2. The first question eliminates one of the 2 partitions. The second eliminates the innocent suspect in the uneliminated partition. So break the suspects up in 2 groups. Say, is the guilty person in this group or the guilty person in that group? If the witness says it's in this group, then you again ask the second question, which of the 2 is guilty, and you're done. Okay, if we go with that particular thought, then with 8 suspects, the minimum number of questions for identification with certainty is 3. Think about it. With 16, the minimum number is 4. And here is a graphic of the result. So here's the minimum number of questions. Here are the number of suspects. And here are the minimum number of questions. And this is a graph. Let's think about role of base 2 logarithm. First, we notice the number of questions increases with the number of suspects, but not as fast. The increase is a logarithmic function of the number of suspects. More precisely, since log 2 is 0.69134, we just have the following. 4 is log 16 over log 2, which is log 16 to the base 2. If we had 8 suspects, we have 3 questions. That's log 2 to the base 8. And we go. So you can see how log 2 has entered into this particular picture, and you can see how log has entered. It's the number of suspects assumed equally guilty and minimum number of questions, and there you have this relationship. We can generalize this very easily. If the number of suspects is n, then the minimum number of questions is log n to the base 2. But this result is dependent on the fact that the partitions are of almost equal size and always 2 in number. So the almost equal, if the number of suspects is odd, you break it up differently. You break it up into, if there are 15, you break it up into 7 and 8. But if they are even, then the partitions are of equal size, and there are always 2 partitions. Now, suppose the witness were allowed to declare up front as to who the culprit is, then the prosecutor is spared the burden of asking so many questions, and in so doing, the witness has conveyed log 2 to the n units of information to the prosecutor. That's how the idea of how the idea of information arose. How many questions do you need to ask? You know, and the amount of information is how many questions you avoid asking. That's how here the unit of information is the number of questions to isolate a culprit. When two suspects assumed equally guilty face a prosecutor, this is of course log 2 to the base 2, which is 1. So the unit of information is called a bit, but here's something more interesting. With log n to the base 2, there is something more interesting to note, because this turns out to be a stepping stone to the notion of information in any random variable. Specifically, log n to the base 2 is log 2 1 over n, and 1 over n is the probability that any randomly chosen suspect among the L guilty ones is guilty. Thus, for suspect I, log 2 is 1 over the probability is the information communicated to the prosecutor either by questioning or declaration by the witness. So this is how log n to the base 2 gets slowly moved towards what Shannon was proposing. Then I call it the Hartley-Shannon leap. The above are simple and reasonable arguments, but it's uncommon to assume that all n suspects are equally guilty. To the prosecutor, some could be a priori more guilty than the others. Of course, the prosecutor has suspicions. So suppose that Pi is the probability that the suspect I is guilty, with all the Pi's possibly unequal, then motivated by the previous development and with a leap of faith, the units of self-information a witness conveys to the prosecutor in pinpointing I was simply declared by Shannon as log 2 1 over Pi. So he went from the equally probability guilty case to the unequal guilty probability case and just plugged in this particular number. That's what I think he did. I may be wrong, but that's what I think he did. Shannon's bigger leap. He took a bigger leap. Why this choice? It was challenged by Barnard. Barnard challenged it in a paper that he wrote in JRSS B, I believe, which is difficult to read. Barnard is always very difficult to read, but I think he kind of questioned it. And Rainey, when he wrote his famous paper, followed up on Barnard's concern. Well, the second concern, with n guilty suspects, the weighted average of the self-informations weighted by their PIs is per Shannon this quantity. So he took the weighted average of the PIs. Okay, so he got this expression, completely independent of what happened in physics. It was termed by Clausius and Boltzmann as entropy. And so this formula appeared to be also in physics. Therefore, it is now called Shannon's partition entropy, and there is an amusing story involving von Neumann that is associated with this label. The rumor or the story the physicists say, and I'm told it's corroborated, is that Shannon and von Neumann were flying to a meeting, and Shannon told von Neumann, I have this formula, what do you make of it? And von Neumann looked at it, said, well, this is a formula which appears in physics, why don't you call it entropy and nobody will bother you? So he just started labeling this as entropy. So this is called Shannon's entropy. But what does Shannon's entropy really tell us? What does it say? Kolmogorov provided a way of articulating its spirit as well as that of... So I think Kolmogorov gave real meaning to this. And specifically with n potential suspects, the prosecutor encounters an omnibus uncertainty of this much. So this is the total amount of uncertainty. And why is that? Upon identification of the culprit, this uncertainty gets eliminated, and in so doing communicates to the prosecutor is negative as the amount of information. Thus, entropy was to Kolmogorov a proxy for the amount of inherent uncertainty in a random variable. So the idea of uncertainty in the random variable measured by entropy, which most statisticians buy, probably goes back to Kolmogorov's famous paper. So questions about Shannon's choice. Whereas the above...
What was Kolmogorov's contribution?
There is a paper that he wrote.
What you were describing there didn't really get into the substance of what Kolmogorov contributed.
No, the interpretation, yes, there's something else he did. He pointed a flaw in Shannon's formula. I'll come to that.
But go back.
Yeah.
What is he adding to that slide, your previous slide?
Oh, connecting entropy as the amount of information in a random variable.
The amount of uncertainty.
Sorry? Uncertainty. About the uncertainty. Kolmogorov's idea was entropy measures uncertainty. Thank you.
Already said that.
I don't think Shannon said that. I'm not sure. Okay, but there's a nice paper by Kolmogorov published after the meeting. There was a famous meeting in MIT. He couldn't be there. He published afterwards, but he did something else I'll point out. Okay? Again, I'll be scratching the surface. It's a difficult paper to read. So the above ideas form the basis of breaking the Enigma code by Good and Turing. Fundamental questions remain to be answered. Why should I2I, the self-information, be log 2 1 over pi? Why should it be like this? What does I2I represent in the case of unequal probabilities? When the probabilities are unequal, it cannot be the minimum number of questions to pin down the culprit. Why the weighted average? Why not the geometric or the harmonic average? Okay, so these are the questions that arise, and the archetypical responses to these. So the first argument is rooted in three arguments. One is tradition. Hartley suggested it. That's not a very good argument, but Jack Good had some nice things to contribute here. For Good, this choice satisfies a psychological primitive, namely a surprise outcome, something having a low prior probability of occurrence, is more informative than that due to a highly anticipated one. This is the picture. If something happens that you didn't expect to happen, then you got a lot of information. If something happens that you expected, then you don't get information. So Good's idea was to essentially connect this log e to the pi. This is the self-information when I is relieved, or the value of observing x equals I. He says if the probability is small, the information, self-information is large, and it goes down, and he says this satisfies a psychological primitive. I think that was Good's idea, but there was another paper written by McCarthy and published in the Proceedings of the National Academy and certified by Shannon. He talks about the measures of value of information and concludes that it's only the logarithmic function of pi or any linear transform of it that uniquely ensures that an assessor of probability is honest. So that means somebody who declares probability is honest if the person's utility is only a logarithmic function. So McCarthy built on Shannon's idea, but essentially closed this loop in terms of so McCarthy was preceded by Good. Its merit stems from the fact that it spawns the viewpoint that information can also be seen as a utility in a decision theoretic context. So this is where it all becomes quite interesting and more modern, that if you look at information as a utility, then of course everything can be justified. in a decision theoretic context.
So is McCarthy correct?
Yeah, I think.
So nowadays we hear
I can't comment, but I think he's correct.
So there's these proper scoring rules,
That's right.
and you know,
I'll come to that.
that's only one proper scoring rule.
Exactly.
The way you wrote it, it makes it sound like he thinks it's the only proper scoring rule.
Oh, well, the logarithmic rule ensures honesty.
But the Breyer score might also. So,
I'm not sure. I'll tell you what.
so what?
For squared error or whatever. Yeah.
So, I mean, I don't remember this two-page paper, so I'm not sure if he's talking about something else, but I wanted you to clarify that.
Yeah, I can clarify to the extent that I think that that's what he said. It's only a logarithmic scoring rule that ensures, and he proved it, okay?
Okay, so I think that
We need to go back,
we'll take
okay?
a look at what he actually proved.
Yeah, okay.
So what does it mean to be honest?
Oh, you asked me what's the probability of rain tomorrow, and I think it's going to be 0.75. But I have a suspicion that you think it's 0.6. I want to please you. So I lie and say 0.6. I don't declare my true probabilities. That's the scoring rule, you know.
Okay.
All right. So to enforce honesty, you know, the McCarthy's idea was long, but I think the idea was good also. I think. Let me get back to this, Glenn, because something else is coming up which is related to what you're saying. The idea of extropy can be essentially about the weighted average formula. This formula, as a measure of uncertainty, is based on convention that a weighted mean is routinely seen as a summarization of uncertainty. Why did Shannon take this weighted mean? Seems like a question. However, there are two caveats in so doing. First, this is where Kolmogorov comes in. The continuous analog of the weighted mean, namely this. So if you just take this formula and take the continuous analog, you get this expression. Was discarded by Kolmogorov as lacking in interpretation, it in general being non-existent, and mathematically always infinite. So Kolmogorov entered the picture here by looking at the continuous analog. I mean, first he kind of, you know, gave this view that it's the amount of information communicated. Now, as Glenn says, Shannon may have done it too, I don't know. But he certainly came upon this formula, and his first page essentially discards this, and he said that really one should think in terms of relative entropy, and this formula is relative to a uniform distribution. And that goes back to the Kullback-Leibler distance, which is this divided by the other one, Q of x. But the idea of relative entropy was essentially pointed out by Kolmogorov. So the second question, and this is what was also interesting to me, what does the mean mean? What do we mean by the mean? The second caveat pertains to the matter of what is the mean value of a number's x1 through xn. This was addressed by Kolmogorov and Nagumo independently, who defined the mean as an infinite sequence of continuous, symmetric, and increasing real-valued functions of this kind. And I won't go through the details. These functions have to satisfy a reflexive law, a certain associative law, and Kolmogorov and Nagumo said that these are necessary and sufficient conditions for the existence of a continuously strictly monotone function f, such that f is given by this. Okay, we will have to read this paper carefully. Difficult to read, but here is a summary. F is called the Kolmogorov-Nagumo function, special cases of which yield the arithmetic, the quadratic, geometric, and harmonic means. And here it is. So if the function, the Kolmogorov-Nagumo function, is like this, then we get the arithmetic mean. If it's like this, we get the quadratic mean. If it's like this, we get the geometric mean. And if it's like this, we get the harmonic mean. Shannon's choice for entropy is this function, namely this one. Well, Shannon could have used any of these as his measure of information and entropy, but he used this one. Of course, also DeFinetti and Kitagawa extended the Kolmogorov-Nagumo work, and they added weights. So the general form of the mean value function is like this, which is what Shannon's formula is. So the Shannon-Renyi choice of f of x, whereas Shannon's choice for his entropy formula is the Kolmogorov-Nagumo function f of x, Renyi in 1961 considered the exponential function. So Renyi's paper uses this kind of a function for his formula for entropy and information. And the question is, under what argument can Shannon's choice of the mean and Renyi's choice of this for the entropy be defended? How can you defend it? Oops. How do you go back? How do you go back?
Use the arrow should work, and the left arrow on the keyboard.
Oh, okay. Yeah. Okay. All right, so here everything seems to come together. But Kolmogorov and Nagumo, there are many choices of fx for a mean. The choice fx equals to x leading to a weighted mean is the Shannon entropy. So how do you justify taking expected values? So justification for taking expected values lies in decision theory, wherein the optimal decisions are those that maximize expected bounded utility. Thus, a way to legitimize Shannon's entropy formula, namely this, is to interpret self-information as a utility in choosing pi as a decision when the state of nature is I. So, taking self-information as a utility, Shannon's formula gets interpreted as the expected utility in choosing as a decision the probability function pi as a decision maker's encapsulation of the uncertainty of x. Okay, so I don't know if this makes sense, but I think that if you look at information as a utility, then you can defend Shannon's formula as an expected utility in a decision theoretic context. Interpreting entropy as an expected utility also paves the path for using the negative entropy as a score function for calibrating forecast distributions and assessing model choices. This in turn spawns the notion of extropy, which supplemented with entropy enables a more complete total score function for evaluating statistical models. So the expected utility comes through looking at this. The extropy, the notion of extropy comes if we look at Shannon's formula for information as a utility. Suppose that p sub x is a predictive distribution of x, and suppose that x star is the actual realization of x. Then log 2 p sub x star can also be interpreted as a penalty score or a disutility in specifying the choice px star when the state of nature is x equals x star, and the negative of Shannon's entropy as the expected penalty score in specifying the distribution of. So this is the logarithmic score as opposed to the Breyer score or the quadratic score or others. You know, it reappears in this particular form. So here is the disutility. So if when x is equal to x star and you have specified p of x star, then this is the disutility in specifying, in specifying x when in fact x star has occurred. Under this setup, the score materializes, under this particular setup, the score materializes only under x star, the event which actually occurs via its px star. other declared value of px for x not equal to x star do not contribute to the score. So you get only scored if you hit the target, and you get rewarded, and you get penalized if it doesn't. But suppose you specified neighboring values with high probabilities, shouldn't you be also rewarded that you came close? That's the whole idea. And if we consequences of not scoring unrealized events. Suppose there are two predictive distributions for x, say px and qx, wherein px star is equal to qx star, but px is not equal to qx for x not equal to x star. Under the scoring scheme, should x occur as x star, both predictive distributions will receive the identical score or will garner the same utility. To account for the feature that when x reveals itself as x star, one also learns that x is not equal to x star, for which these probabilities have been assigned. Excuse me. The scoring system needs to be made more complete and equitable, and this is the roadmap to Extropy. So I think the matter of not scoring unrealized x may be germane if closeness to the revealed x star is also a figure of merit, which may be relevant in certain applications like target tracking. More generally, in communications, one learns more than this quantity when x is relieved at x star because of prior probability assignment, as indeed, I'm fine. Has indeed been made for, you don't have to.
Okay, that's all right.
Sure. Sorry. So here is the disutility score when x is not equal to x star. Analogous to choosing log 2 to the px as the penalty score when specifying px and observing x equal to x star, we take minus log 2 as a penalty score in observing x not equal to x, having specified px. So if we do this, then assuming additive utilities and scores, you get a more complete scoring by scoring using the log px and also the log 1 minus px. And that's something that, something new that I hit upon. So the expected total utility is the Shannon entropy of px plus the extropy of px. Similarly, the total score or disutility is this one. Thanks. Thank you.
Have you defined extropy already? Did I miss that?
Sorry?
Have you defined extropy already?
I'm going to define it, but I'm motivating it.
Cool. Okay.
What I'm saying is that if you use the logarithmic score and Shannon's formula as a scoring rule, you are not scoring things that you came close to but you never hit.
Yeah.
So if you ask me what's the price of a stock tomorrow, and I say it's I give a probability 44 and tomorrow it occurs, I only get rewarded if it actually occurs, based on what I said. Right. But here, if I'm in target tracking for communications, it would be a price. Okay, so I'm going to. So this is the Shannon extropy you asked me. Here's the formula.
Cool.
So Shannon entropy is this. Shannon extropy is this.
Oh, okay, I see.
And how do you motivate it? And the way you can motivate it is by looking at it as a utility. And that was slightly what I did. The rest of it is all around. But the guy who wrote this is, I'm sure Glenn knows him, he's Frank Ladd. You know him?
Oh, yeah.
You do?
I don't know him. I know his work.
Oh, he's quite a character.
He's an Australian, right?
Yeah, he's an American.
Oh, he's American? I thought is Australia?
New Zealand. He lives in New Zealand.
He lives in New Zealand, okay.
Yeah, he does very interesting work. He's doing some work in quantum theory now.
Yeah.
It's very difficult to follow him, but he has a paper in statistical science, and
He does this?
this is where he introduces it. And I invited him to GW. Well, he was passing through Washington, so I asked him to give a seminar. He gave a seminar. I didn't quite understand what he was saying, but later on I followed up.
Is this whole difference here, is that going to be a proper scoring rule as well? I mean,
Yes, it is a proper scoring rule.
Yeah.
It's a proper scoring rule. So he's essentially expanded the idea of score. Well, he just did this part.
Right.
He worked on, he looked at this Shannon's formula, and he made comments, but he never quite got into the why of Shannon's formula. He made some comments, Shannon's third axiom and all. Then he arrived on this, and he said this is a better way to score. But I asked him, why do you use this formula? And he couldn't answer me. And I couldn't also answer why this formula. I said if it's unequal probabilities, then this formula doesn't make sense. And I want to show you a few simulations by which I'll show you that this formula underestimates the true information or entropy. Okay? So the contribution was to interpret this as a utility, which was done by Good and what's his name, McCarthy. Mostly by Good, And then I asked Frank, what is the meaning of this formula? And he couldn't. He said it works, it gives me better predictions. So once I connected this with this as disutility, the explanation quickly fell out from decision theory. So here's a simple example. Here's Shannon's entropy. So suppose your prior probabilities are exponentially decreasing. So the first suspect is most guilty, the second suspect is less. So here's Shannon entropy using Shannon's formula. If you use the weighted average, you get this. If you use the weighted geometric mean, you get this. And if you use the weighted harmonic, you get this. Clearly, Shannon is overestimating the entropy. We don't know. Change the formula, you get a different answer. But I'll come through this later on. Okay, I'm going to skip this because Rennie has a lot here. And basically what Rennie does is he introduces improper distributions and all things that essentially are not maybe good for mathematics, but not good for intuition. So he says the entropy of a generalized point function is 1 over px. Generalized point mass is 1 over px. So I'm going to just skip this for the time being, but I'm going to talk a little bit about Shannon's entropy. The first thing I want to say, that in the case of equiprobable suspects, so this is kind of a summary, in the case of equiprobability suspects, the self-information is the minimum number of questions to pin down the culprit with certainty. Okay, we buy that. There's no such motivation in the case of unequal probability.
Yeah, so isn't it also the expected number of questions?
Well, this question is, what does expected value mean?
Well, okay.
That's the Kolmogorov-Nagumo function. Kolmogorov-Nagumo would say you could check expected value,
Okay,
and so, okay, got it.
Well, yeah, what I mean is just like if I have a random variable with a non-equal probable distribution, and I get to ask yes or no questions on a partition, even partition over and over again, that if I repeat that experiment a bunch
but we don't want to do that.
Okay, sure, but okay.
Okay, but if you look at it from a decision theory point of view, then of course what is this? Von Neumann, Morgenstern, and Savage, all those results say the expected value is the optimum decision.
Right.
Yeah. So at least we can justify it. So what I'm saying eventually is that Shannon's formula can be justified. Depends on how you interpret it. If you interpret it in this way, you also get the extropy, and then you can pull in Frank Ladd is that. But okay, but it's debatable. Partitioning under unequal probabilities. Motivation for self-information in the equiprobable case was dependent on partitioning strategy, namely two partitions. So, all this simply says that you must partition in two. The minimum number of questions will depend on the partitioning strategy used, and with unequal probabilities, unequal size partitions seem intuitive. So if you know that some culprits, some suspects are more guilty, then you wouldn't partition it in half, which is what Shannon's formula will do. You will partition it differently. How different is different? Okay, so this is the next question. Okay. And of course, the simulation we have done does exactly what you're saying, which you wouldn't do in real life.
Right.
You can't bring suspects again and again. Okay, so I'll show you a few pictures. Since the underpinnings of Shannon's formula are based on equal size partitions for a uniform probability distribution, it results in an inefficiency when the distribution is not uniform. Shannon's formula overestimates a partition-based entropy. Okay, so here are the pictures. So here is the partition. You have an exponentially decaying prior probability. Some suspects are more guilty than the others. So if you use Shannon's formula, this is your entropy. But if you partition based on 0.1, and of course if you look at the arithmetic number of averages, you will get, in all cases, you will get a lower formula for the entropy, but for 0.5 you'll get the lowest. So this is a simulation. Now if you look at the quadratic average, arithmetic average, and harmonic average, then the lowest happens at partitioning at 0.35, but not that much. But 0.5, the harmonic average gives you the lowest entropy. What I'm saying is that the entropy in a random variable changes if you were to motivate it based on what average you use. Yeah.
Sorry, what do you mean by information if it's not? Sorry, what do you mean by entropy when it's not already defined as the Shannon's entropy? What is the true entropy that you're saying?
Oh, there's no such a thing as true entropy.
So how do you know what is?
Well, if you use Shannon's formula, your entropy will be the blue. Will be somewhere here. If you use the quadratic, I'm sorry, it's with the middle one. Oh, sorry. Yeah, sorry. This is what Shannon's formula will give you.
Right.
If you chose the quadratic average, this is what your entropy will be. This is your measure of uncertainty in a random variable. If you choose the harmonic average, you'll get the lowest. But the argument is you must choose this because this has a justification. This and this do not have a justification. You could choose any average you want to.
So when you said that the Shannon's entropy was based on the assumption that all of the answers were equiprobable, were you only referring to the fact that we're taking arithmetic average?
Well, Shannon did two things. Shannon did two things. One is he said self-information is 1 over px, no matter what px is. Okay? His original formula.
I thought it's log 2.
Yeah, yes, log 1 over px. You can defend log 1 over px if all the culprits are equally guilty, if it's a uniform distribution. As the minimum number of questions you need to pin down the value of the random variable, okay? Then what Shannon did is to get his entropy formula, he took the weighted average, weighted by the probabilities, okay? Rennie questioned, and what's his name? Barnard questioned why the weighted average. My claim is you can defend the weighted average if you look at self-information as a utility. And the motivation for looking that as a utility is what Jack Good said, namely, the smaller the probability, the more you're surprised.
So when you were speaking of the equiprobable assumption, that was only
just to motivate.
Self-information when it was first motivated. It was
Exactly. Exactly.
So is there any way to deviate from that at all?
That's what we are trying to do.
But you're only talking about the averaging method.
Well, there are two things. One is the averaging, and one is choosing the formula, 1 over px
What
log.
is a self-information
Right,
unit?
right. So I'm saying that according to Rennie and Barnard and Kolmogorov, you could have taken any of these averages because they didn't think in terms of decision theory. If you think in terms of decision theory, and assuming that everything in decision theory is correct, then you would take Shannon's formula.
So, is the quadratic average, if we're using the quadratic average entropy, is the quadratic average the number of questions I'll need to ask going to equal the quadratic average entropy? Because it does do that for the arithmetic average.
Please repeat.
Yeah. So, if I'm using like the standard arithmetic average,
Yeah.
right? The number of questions by that average that I'll have to ask to figure out the value of a variable will be the entropy, right? But if is that also true for quadratic average? Like if I'm using a quadratic average to weight the logs, does the quadratic average number of
Can we postpone this question?
Sure.
Because I want to show you what happens. For now, I'll simply say that you should use, if you look at self-information as a utility, then Shannon's formula can be defended.
Gotcha.
Okay?
Sure.
Now, what does that formula really mean? Does it mean the minimum number of questions you need to build out a culprit? The answer is no. I'll show you that by a simulation. This is where I'm getting to. Well, forget this. This is when the distribution is U-shaped. But here is, let's even forget this. But basically, here you have exponentially decaying prior probabilities. Shannon's formula will give you this value. If you partition at p equal to 0.4, Shannon's formula will give you this. If you partition at p equals 0.5, Shannon's formula will give you this. So in all cases, depending on where you split, where you partition. So this is a question of how to partition, you know. Shannon's formula assumed that, you know, the motivation for Shannon's formula assumed we partition equally. Okay, so here you will get a different perspective. And the next slide, okay, so these pictures essentially reflect the story, but here is what happens. In reality, if you simulate, if you use Shannon's formula on this axis, and if you look at the average number of questions doing what you said, repeating it, you will constantly see that the entropy is underestimated. Yeah.
So I guess that was my question to begin with. What do you mean when you say entropy is underestimated? So what is it that you're estimating?
You're estimating, it's a reflection of your measure of uncertainty. I mean, there's no, uncertainty is something personal. So your measure of uncertainty, when expressed through Shannon's formula, would be greater than what would actually happen if you did this run after run of simulation.
So, can I ask?
Yeah.
I think to clarify this, I'm guessing with your question. you simulate questions according,
You bring groups of 100 people over and over again, and you have a decreasing probability distribution for your prior probability of a culprit.
Okay.
And
You ask them the question.
as the question, yes, let's say you partition it, right, and you first break the probability into two parts, 50%, and so if culprit number one has 50% probability and the others have the remaining, you just partition at the first culprit and you see how many questions it takes to pin up, because the real culprit could be on the other side, you've given a high probability. So if you were to do the simulation, this is what you'd find out, you know. So to answer your question, it's really a philosophical matter, you know.
Well, but I think there is the concrete answer being that the so-called entropy is said to be the number of questions needed to find the culprit per your simulation scenario.
That's the way I look at entropy.
Okay.
Yeah.
And for the simulation, basically what you have said is the discrete distribution over the finite number of culprits.
Right.
Potential sort of.
Right. So you can say that entropy can be, but I don't know how the engineers interpret entropy and how the mathematicians interpret, you know. Kolmogorov simply said that, or Shannon simply said that if the distribution is discrete, the entropy is px times log 1 over px. No explanation. I'm sure the motivation in Shannon's mind was this. The motivation in all their minds was this. Why did they choose 1 over px was not clear to me.
So in this figure is to say that essentially if you use Shannon's entropy as the measurement, then it is overestimated.
You will overestimate. Correct. Let me just, there are a lot of simulations under different runs, but let's just look at another example. I wrote the bedroom of a 300-pound hawker in New Jersey because Trump declared
400.
He said 400? Well, he's lost weight. So there is a hacker. Now, this is a paper which appeared, or at least this paper appeared in an engineering journal. So there's a hacker, he has several passwords, one of which is correct. And so what the hacker does is order these passwords in decreasing sequence of his or her subjective probability of occurrence, and then tries each password one at a time in order of their probabilities, you know, till it goes. So the hacker has 10 passwords, ranks them, tries the one first with the highest probability, then he tries, you know, keeps trying till he succeeds. And the bottom line result is that Shannon's formula gives a lower bound on the average number of trials by the hacker by this formula. So the hacker is not very efficient, even by Shannon's formula. The reason behind this inefficiency is that the partitioning strategy is not optimal. The hacker is partitioning one and the others.
Right.
But if the hacker partitioned based on p equal to 0.5 is what we find is the best way to go by simulation, then you know, he would or she would catch it fast. And that is, so I say you can conquer only if you divide wisely. You know, conquer, divide and conquer. You have to divide wisely. That's basically the way. Okay, I don't know, I think I've jumbled a lot of things, but I'm going to stop at this point. There are ways to change it, as Glenn suggested. One idea is the witness is dishonest. The other one is, what is it that you suggested? I forget. When we started, you suggested something. I said there is a possibility.
I've forgotten to.
Happens. So I'm open for any other comments.
With the hacking, you said divide the passwords in half. What does that mean? You pick half and you try them all at one time? Or?
Oh, no. You follow the partitioning. Yeah. You would break it into two parts.
Okay.
And then you will try one.
Okay.
But it's not clear how will you, because there's nobody. Well, yeah, you would. Not sure. I have to think. How the hacker can use. All I showed is that the hacker strategy is not optimal.
Sure. Yeah, that's fine.
But I don't know what the hacker should do.
Okay.
I have to think. Okay, thank you.
Well, but so it seems to be that if the hacker, usually in the usual setting, you can only try passwords one at a time.
Yes.
But
That's the problem.
Yeah.
That's why I have to
It
think.
seems to be that, because you're talking about the Shannon entropy being a lower bound, it seems to be that had it been the case that there was a special distribution over the set of possible passwords.
And there was somebody telling you which is the correct password.
Yes,
Somebody
then
answering.
This would be
Then this would be, yeah.
bound or
Yeah,
even
yeah,
something.
yeah. Okay, the point of that was to show that the hacker strategy is not optimal. Okay?
But given the constraint that the hacker could only try one at a time.
That's right. That's right. That's right. That's right. But in the courtroom, you have a witness. You can say, is the culprit here or there? And
Sure.
the expert says, no, it's there. So if the hacker had some way of finding out where the password is, then it would work. Okay. I need to think a little bit. Okay.
Well, just a different example they can give. You can do multiple blood tests at once, mix various samples together, and then see if it works. If it runs positive, and then check that set of blood samples instead. Just giving a different example.
Sure. So
That
what
would be a bit more.
more fundable?
Yeah.
What did you do?
So it's something that one of my stats professors told me before. You mix a lot of different blood samples together, and then you try the blood test on that very big blood sample, and then you obviously have a different sample on the other side. And if it's
I see.
negative, then you discard that and then try to.
Oh, that's a good example.
Mm-hmm.
Write it up.
So I'm sorry, did you say before that the entropy underestimates the average number of questions?
That's right.
It overestimates.
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 So now, how does Extropy, can you,
Extropy is very good only for comparing models. Okay? So if you want to score a forecaster, if you score the forecaster using the logarithmic score, which is like the entropy score, then you only reward the forecaster based on the probability that he assigned or she assigned to the event which occurs. But you may want to reward the forecaster for forecasts which came close to the real one. For some reason you may want to, let's say you're comparing two forecasters and one is always coming close to the right answer, closer to the right answer than the other one, then the extropy and the entropy together can be used to evaluate the forecaster. Okay. So, okay. Do you have a question?
So I guess I'm not sure whether I always follow the thread, but if the probabilities are not equal,
Yeah.
then you're going to follow special strategies for how you partition to ask the questions. Is that
That's right. But the bottom line is it turns out to be partitioned by 50%. So if the probabilities are unequal, so let's say the first three culprits, probabilities add up to 0.5.
Yeah.
And the next 30 culprits, probabilities add up to the remaining 0.5, then you partition not at half, but you partition the first 3 and the next
You make sure that the first 3 are
form a collective.
form a collective in your first partition.
Yeah, and the rest in the second, rather than,
But then what if we say yes to the first 3,
oh, you'll get to the answer faster.
but then you can't do a 50-50, then you've got to do it
After the first 3?
after
the
it says yes, it's one of these 3.
Yeah, well, then you renormalize your probabilities.
And then it's a third, a third, a third, so you can't do a 50-50 split.
Those are also decreasing in your simulation.
In my simulation, they're decreasing.
What's decreasing?
Yeah.
If you would order the probabilities that you put on the finite numbers of suspects, and then you just start with the top ones.
Yeah, but what I'm saying is you can't always ask 50-50 questions.
Yeah.
You can't always split 50-50.
Because after the first step in this example, you can't.
You cannot, but then you will split 2 and
You can.
2 as closest as you can.
Yeah.
So that's
And did that lead to a justification of Shannon's formula?
no justification for Shannon's formula only came by looking at the self entropy as a utility.
So Jakob Bernoulli, when he first, in his book, when he was talking about looking at equally likely cases,
Yeah.
he had a paragraph where he says, well, of course, things aren't always equally likely, but
Yeah.
we can always reduce them to the equally likely case by
Groups.
making one case
Yeah.
more equally likely,
Yeah.
give it 3 equally likely cases instead of just one. So that we can actually think of everything in terms of equally likely cases, even if they're not equally likely. He says that at the very beginning of probability theory, we get that.
Yeah. Well, then,
So-
if you did that, you'll be asking more questions before you caught the culprit.
Well,
So,
Yes, you could. But the idea is that if you took the 50, yeah, which is what,
but it seems like Shannon's formula approximates still what you would achieve
Yes.
by your splitting.
Shannon's formula is a
You
good,
don't have to go to the utilities. I don't see that you have to go, I mean, it's always going to be approximate, but I don't see why you have to go to the utility theory in order to justify.
how do you justify expected values? How do you justify expected value?
Oh, we heard over here, it's just the long-term average if you behave like this in the long term.
Well, but with utilities, it's a clean argument, I think.
That's clean.
I don't know. I think it's, well, I was trying to connect what Good said about utility, and I was trying to collect the expected value formula. I was trying to answer, what is his name, Barnard and Rennie. I was without going through Rennie's machination. I thought Rennie had, have you seen that Rennie's paper?
No, I don't remember.
It appeared in the Berkeley Symposium, Berkeley Proceedings. Very well
I'm sure I
cited.
saw it, but
Yeah, very well cited. Very well cited. Yeah. Yeah.
also, if you take like 4 equal probable cases, does have a higher entropy than
That's
equal
right.
probable cases.
That's right.
Yeah.
The uniform has the maximum entropy.
Yeah. Yeah. And uniform with 1,000,000 has higher entropy than uniform with 1,000.
Yeah. But yeah.
So I still feel like the way that we can justify it, I haven't really thought about this like in that way. It's kind of just something I've believed for a long time, and like every time I look at it on paper, it looks right. But I still feel like the way to justify it is that it's the expected number of questions. And in fact, like when I read it in textbooks, like when I read that kind of justification, I never read the minimum. I always read the expected number of questions.
Yeah. I think that paper by Kolmogorov and Nagumo essentially tries to answer the question, what do we mean by the mean, which is the expected value?
Sure. Yeah.
And he said, well, it's a kind of a function with these properties, and depending on which function you choose, you get the arithmetic average, the harmonic average, and all. So, I mean, that's going a little beyond the intuition that we are.
Okay, so one way to put the question would be, why would we use the arithmetic mean as opposed to some other mean?
The harmonic mean.
Sure.
And you notice with the harmonic mean, the number of questions comes down.
Right, but what I'm trying to, okay, so this is what I was trying to ask before, right? So if we use the arithmetic mean as for the entropy formula, then the arithmetic expectation of the number of questions I need to ask is going to equal the arithmetic entropy. Is that going to be true if I use a different mean also? Because if it's not, that seems like a pretty good justification.
Yeah, I'm not up on it. Maybe I need to ponder the matter. So what you're saying is,
if you use the arithmetic mean to calculate the average number of questions that you need to ask, that's going to end up equaling the arithmetic mean entropy.
no, it's less.
It's less.
That picture I showed you, on the x-axis is the entropy formula, which is the average. And on the y-axis is the average number of questions. So that is,
so it's less.
it's less. And so if you use the geometric mean, it'll be still less. Except with the geometric mean, I wouldn't have a justification. I don't know how Glenn would justify it. How would he justify the geometric mean, Glenn? How does one justify the geometric average?
I'm not into doing that. I thought the arithmetic mean, I agree, the arithmetic mean is where, you know, probability didn't start with probability, it started with expectation.
Yeah,
So the mean was there before the probability was there.
I'm sure of that, yes, because there is a book, Probability by Expectations.
Yeah,
Right.
that was the original, Huygens used, Huygens had expectations, not probabilities.
Yeah.
So,
Well, you're going a little deeper than I can go.
So I'm sorry, in that simulation where you did that, because I feel like I can prove that the average number of questions, like, I feel like I can prove that the arithmetic mean of the number of questions is going to equal the entropy.
That's what I showed that it's not.
By simulation.
Yes. Oh, I showed it by simulation.
yeah.
Absolutely. I couldn't fix the formula to get but I didn't work hard on that.
Yeah.
But if you can do it,
That's really interesting.
if you can do it, then that's a good justification.
Yeah.
so I found the 2-page McCarthy paper
Yeah.
on Google Scholar there.
Yeah.
It doesn't seem to do quite what you said.
Does it?
It references I.J. Good.
Yes.
He does something much more general.
He does something much more general.
And it looks like he's almost sort of analyzing.
Okay, I tell you what he does. He says any function of the logarithmic will be no. What does he say?
He says that good. Well, first of all, he does something much more general, which almost looks like he's trying to classify all the proper scoring rules. And then he says, in this special case, Good has shown that the logarithm works, and that an unpublished paper by Gleason shows it's the only one. So where in the hell is that? I mean, in other words, there's an historical job to do here to find who this unpublished Gleason is.
Oh, Gleason is a famous physicist.
Well, maybe it's that Gleason. He doesn't tell the first name.
Yeah.
So
he only mentions logarithm with respect to like a one sentence about I.J. Good, and
Yes.
about Gleason being the one that showed it was the only one.
well,
So this notion that he's showing something about log being the only one, he's not.
But I think
Reference.
Good may have made that.
Well,
Okay, so maybe I'm wrong in giving credit to McCarthy.
Well, I'll read.
Take a look at McCarthy.
Yeah.
I've looked at it. I
So
forget. I think it's a
McCarthy
bit more general.
McCarthy says, I.J. Good considered the problem of paying the forecaster with the restriction that the payoff depend only on the probability assigned to the event which actually occurred. He showed that the log keeps the forecaster honest And Gleason, parenthesis unpublished, show that this is the only function which does.
Well,
Okay.
that's not true, right? There are other proper
I thought so.
scoring rules. There are. Yeah,
Oh, no, there are other proper scoring rules.
Well, so that's the only place log appears in this paper, is this reference to Good and Gleason. And he doesn't show that log is unique, he's saying Gleason showed it. So where is it?
Right.
It does have a unique property that's pretty easy to show out of proper scoring rules, which is that
Okay, but this is where also Kinchin's work comes in, because he also glorifies the log, basically. That is Shannon's third axiom or something.
So maybe there's some real,
Yeah.
maybe there's somebody who's really done the history of this.
All right. I'll go.
There's a theorem that precedes what you just read, which says the payoff rule keeps, this is McCarthy's words, Theorem 1, the payoff rule keeps the forecaster honest if and only if the function fi of q equals to the derivative of f with respect to each of the individual qi's as arguments.
So there's nothing in there saying a logarithm.
No,
is
of course
unique.
not.
No,
He
it's-
said, but this is but I'm saying that this seems to be the framework under which McCarthy is setting up the honesty argument,
Yeah.
and log being one of the functions. That
Oh, so log is not the unique.
Well, the Gleason, well, he's citing Gleason, which is true. I mean,
Yeah.
probably meaning that he buys that argument.
Yeah, but there's something more in. But now that you guys raised the question, I need to go check up as to what Chinchin has said, because there are some axioms which Chinchin has taken up from Shannon.
Yeah, so I just want to say, because, so there is one property that log has as a proper scoring rule, that it's the only function that has it, which is that if there are two trials, and I score you on the first trial and then the second trial.
Oh, because it's additive.
Exactly.
Yeah,
if I score
the
you on first
utility is
trial, and I
additive.
score you on the second
That's
trial,
right.
That's the same as if I
That's
was
right.
treating it as one bigger
Yeah.
variable.
Yeah. The log function is additive. The utilities are additive. Yeah, I think so. I think.
So that's not going to be true for the prior score or squared error. Or anything like
Correct.
that.
Yeah, that's right.
Yeah.
Yeah, I'm sorry, I forgot.
No, that's good.
Can I ask you something just about what you said
Yeah.
before? I thought to say anything about whether the Shannon's entropy, whether it would equal to the minimum number of questions needed, that's also dependent on the way that you partition the space.
That's right.
Yeah, there is something, like, I think probably it's going to be something like you need to partition it, whatever the optimal way to have it or something like that is. But I still, like, at least when I look at cases, like if we put up a case, like it's gonna, like, we look at something like with some variable with 4 possible states, and we assign probabilities to them. If we look at the expected number of questions we're gonna have to ask, like, and by that I'm just defining, like, you just multiply the number of questions in each case by the probability of that case occurring, it's gonna end up equaling the entropy.
Oh, I see.
Yeah.
Okay, so that's to say that you don't have, like, even finiteness aside, let's not even think about the number of limited suspects. You don't yet know what is a recipe for asking a question when you do
Yeah,
it.
right.
Okay.
Yeah.
So, I'm not sure, if you can prove that is right.
I'm not sure if I can prove it in general, but I feel like it can't be too hard, because for, like, specific cases, it seems really easy to prove.
Uh-huh.
Like if I have...
Well, for the uniform case, it does.
Right.
Yeah.
Right.
Yeah, for the uniform case, it does.
So yeah, that's an easy
So
one.
what happens when it's not uniform? Yeah.
But if we do a specific case with a specific variable, has, like, whatever, 5...
Yeah, but suppose you look at an exponential case and suppose it's almost uniform. When n is large, then it'll also come close.
Right.
But in the extreme case, I don't know.
Yeah.
I mean, at least the simulations have not.
Yeah.
By the way, it's difficult to simulate this. I mean, not difficult in terms of programming, coding, but in terms of conceptualizing how the simulation should be done, takes a little work.
Yeah,
What's the
My
number-
student did it, so.
What is the number of suspects that you use?
100.
100.
We used 100. My student did it. Well, he's graduated now. Hire him. He's in Hong Kong, though.
And what's the exponential distribution? Is it 1/2, 1/4?
But just 1/2.
So the first one is 50%, the next one is 25%, the next one's...
Well, first one is 50%, then you eliminate, then you have the one that, you know.
I know what I'm saying, but the prior you're starting with over the 100 suspects? Is
Yeah.
it 50%, the first one is guilty, 25%?
Oh, no. It's a gradually decreasing function. Yeah, it's not extreme.
Okay.
Yeah, it's not extreme. Yeah. Anything else?
You can conquer only if you divide.
Sorry?
So divide and conquer.
I'm just curious about the entropy.
Yeah.
So it seems like, so what that formula is doing is it's accounting for being, for either seeing X or not seeing X, or predicting X or not predicting X, right?
Well, you get scored for predicting X. The entropy formula scores you for how close you came to predicting the value that occurs. But if you came close to predicting its adjacent value, let me give you an example. Suppose x equals 3 is what occurs, and you gave a probability 0.5, say 0.6 to x, say 0.7 to x equals, say 0.4 to x equals 3, but gave a higher probability to x equals 4, you don't get rewarded.
By entropy.
By entropy, right. But the extropy gives you some reward for it.
But Extropy isn't paying attention to any particular attention. That formula, I didn't see that. It's not paying attention to the close ones. It's just
Yeah.
No,
No, you're right, it's not. I was thinking the same thing, like it doesn't give you more...
No, it just gives credit to what you did not, rewards you for what.
R ones as well.
Yes. But the entropy formula, if there are two people with two probability distributions, very different probability distributions, except they agree on one point, and if that point occurs, both of them will get the same score.
So what I was going to ask, and I don't know the extent to which this is redundant, but here what you're doing is you're taking, I guess a distribution can be described, I guess you're describing it by the point masses at each
Right.
point. But you can also ask the events of, I guess, the complementary events, which exclude one point. But, I mean, would there be a problem or any benefit or to, instead of going sum over all x, px, the usual formula, and then the opposite for the extropy? I mean, if you just summed over all events, probability of A, log of 1 over, all subsets of the sample space, to define some kind of measure. Does that say anything? Or is that, I mean, this would be taken into account all possible events and how well you did at predicting them.
Well, the entropy looks at all the events, doesn't it? Px times log 1 over px over all x.
Well, no, but it sounds like there's something that it must be missing if you add this point, and that's why you add extropy, right? I mean,
Right. The reason you add extropy is two probability distributions which agree on one point. If that point occurs, they get the same score.
But I guess by that, I'm asking, by that logic, would there not be a situation in which you account now for extropy in which two distributions are similar in certain in certain ways,
Oh.
they would get the same score.
Okay, but what you do is the total score is what matters, not just the entropy score and the extropy score. You look at the sum of the scores.
And that addresses this whole thing.
Seems to address it, yes, because this guy, Frank, has done a lot of simulations with economic data and seems to have claimed that. My objective was to give an interpretation of extropy. My focus was to give for a long time I struggled with why this extropy. So Frank's answer was, look, I have done it, and I've compared all these, and I come up ahead. He does better, his predictions get better scores. So my objective was, how do I explain this formula? Having understood how Shannon's formula appears, I tried to understand how the other one. And so I said, if I look at Shannon's formula in the context of utilities, all right, then not only can I, explain the formula, but I can also explain the extropy. So my objective here was not to make a case for extropy, but try to understand what it means. That was my objective. It's a paper worth reading. It takes a long time to read because he doesn't write well. You know what I mean? He writes in a muddled way. Yeah. So that that makes the reading a little hard.
Any other questions?
I'll tell a story.
Yeah.
So in my youth, I was an associate editor for a journal, and I rejected a paper by Frank Ladd.
Uh-huh.
And I've always regretted it, because I thought it was more interesting than the papers I accepted in that role.
Why did you do that?
And here was Frank Ladd, the referee. I couldn't find a referee that liked the paper. But it's still, the interesting thing was that the papers that I thought were stupid are the ones I remember, not the ones I thought I could publish. So here was Frank Ladd's idea. Frank Ladd's idea, which he later published in a book, was that a Bayesian is always calibrated. Did you ever hear this from Ladd?
No.
A Bayesian should not worry about being calibrated.
Automatically
He's
calibrated.
always calibrated, because here's why. Let's say a Bayesian says, okay, it's a fourth probability, this one, or this, there's four things,
Yeah.
four possibilities. And the Bayesian gives probability 1/4 to each one.
Yeah.
Let's say one of them happens. And you say, okay, how many of the Bayesian's predictions were right? Well, let's look at how many 50-50 predictions he made. He made a 50-50 prediction that it was A or B, or that it was A or C, or A or D, or B or C, or B or D, or C or D.
Yeah.
Those are always 50-50 predictions. Half of them are right, no matter what happens.
Well, no matter what happens.
And you can generalize
Yeah.
that to anything you want. The Bayesian is always calibrated. Half of his 50-50 predictions are right. Half of his 75 predictions, 75% predictions are right.
Yeah. So,
By
yeah.
not saying anything, you're always right. There isn't just, you're never
Whatever he
wrong.
says.
Whatever you say,
Bayesian says something, but whatever he says, he's
But I
calibrated.
know, but if you did not say anything, it says that everything that you did not say is correct.
It's correct. Yeah. And things
Oh,
like
no, that was a different paper.
yeah.
That was-
Okay,
Can we call it a day?
Yeah.
Yeah, thanks.
So
Yeah.
we-